when we look at the calorimetry, okay, and I gave you a sheet, what we're looking at is a reaction inside a cup. Okay. And so the reaction sits inside here. Okay. And really a lot of chemistry happens inside water, especially in the undergraduate and the freshman year. So we have chemicals inside that water and we mix them together and something happens. All right. Now, in that, we have to describe the equation that happens. We have to describe what the states of matter in that reaction are happening. But one other thing that we need to describe is the energy flow in that reaction. And so the reaction are the chemicals. Everything else is the surroundings. The system is the chemicals. The surrounding is everything. And really, this reaction happens in water. So the water is going to do one of two things. The temp will rise, or the temp will fall. There's one option, one more option. The temperature could rise, the temperature can fall. What's the other option about the temperature? The temperature stays the same. Why can it not be the temperature stays the same? Why can it not be the temperature stays the same? What did I define first that happened? A reaction occurs. If no temperature changes, then you have no what? No reaction. Okay? And so a reaction is going to occur, we assume. If a reaction does occur, there is going to be a temperature change because energy must flow when a reaction occurs. Okay? Energy can even flow if a state of matter changes. Some of the physical properties can cause energy to flow, and we'll take a look at a couple of those also. And so what we're going to be doing is measuring a temperature initial and a temperature final to deduce what's going on. All right. Now, to get energy, all right, we use a couple terms. One of the terms we use is Q. Okay. And Q is the term for energy. There was a term, the energy E is equal to Q plus what? There's one more term that energy is associated with. Do you remember? W, which is what? Work. But because we're in general chemistry, your reaction doesn't roam around, and so the distance it travels is 0, and so work is 0. Okay, so we're just concerned about Q. Q is equal to, in a calorimetry problem, inside the cup, equal to three things that are multiplied. C, mass, change in temperature. That is the equation that drives the calorimetry in the cup. Okay, and I wrote that on the piece of paper at the top. It says Q equals C M delta T. Now, if I articulate that a little bit better on the piece of paper, what does C represent? It represents a specific heat capacity, which is some sort of number that has amount of energy for every gram times every degree change. It doesn't matter if it's Celsius or Kelvin, because if you take Celsius minus Celsius and Kelvin minus Kelvin, they will come up to the same answer. Okay, So that has to be something that is given, or if we are given everything, we can actually derive that one. Times the mass of the solution. Now this will be important when you get to CHEM-111. The solution a lot of times will tell you what it is, but remember, a solution is made up of two things. It is made up of the solute plus the solvent. Oh, CHEM-111 is going to be really hard on some of you. It may give you the mass of the solvent, but it won't give you the mass of the solute, so that might be your X. Okay? And then the change in temperature is always final minus initial. Okay? Now, you multiply, really, if you get specific heat and you get a mass and you get a change in temperature, you multiply two things together. Mathematically, that is not hard. Okay? We hope. Okay? Multiplying three numbers together. But this is where it gets hard. You have to think about that number. And so after the calculation is complete, this is the hardest part. It's not that hard, but it actually makes you think, and most people don't like to think. I just want to put what's on the calculator into the box. And it wants to be green every time, not red. Right? Okay, so you have to decide whether to add a negative sign or not. And that depends on what the question really asks. If you are talking about the energy derived from the reaction, you have to put a negative inside of it. But if the question is involved in terms of the solution, whatever you calculate is what the value is. Okay, here give you a couple examples. I said some ifs. If by chance the temperature final is higher than the temperature initial, okay, so what happened? Your solution heated up, okay, because it got hotter. All right, then the answer that comes up is going to be positive because the solution was heated. The solution added energy because it got hotter. So the Q solution will be positive because the solution must gain heat to increase in temperature. But if that actual question talked about the reaction, okay, the Q reaction will be negative because this is what happens. You must add the negative sign to the calculated value because the reaction gave off the energy which was absorbed by the solution, which caused the solution to increase in temperature. Okay? So if it asks you about specifically what happened in terms of the reaction, to heat the solution, it needs to give off energy. If the question asks you about the solution must absorb the energy, it must be positive. Okay? On the other hand, if the initial temperature is higher than the final temperature, then that calculation is negative. That will make the three things multiplied together negative. Okay? And the solution was cooled. The Q of solution will be negative because it got colder. The solution gave heat to the reaction and it got cooler. If you're talking about the Q reaction, the heat of the reaction, it really needs to be a positive value. So you must add a negative to the calculated value because the reaction had to absorb that energy, had to add that energy to itself so that the solution was cooled. Okay? And so this one, you just can't put it in the calculator and see what you see on the calculator because sometimes it'll give you a number. Sometimes it's positive, sometimes it's negative. You have to interpret what is the question asking, and answer that question. Okay? So, gave you a little bit of that because it's a little bit thinking. All right, I'm going to do a couple examples. And a large bed of rocks are used in some solar heated homes to store heat. Okay? All right, so the reaction in this case is solar heated. Okay? The energy is coming from the sun. The bed of rocks is our solution in this case. Okay? If I interpret it. Now, I don't go into the lab and put rocks inside the beaker, but in this case, what's absorbing the heat or giving off the heat is the rocks. Okay, just like the water would be. So that's the solution. Okay, assume the specific heat of the rocks is this. Oh, I have a specific heat. Great, I have a specific heat. Calculate the quantity of heat absorbed by this amount of rocks and a temperature change that was 12. Okay, so I have the Q, is equal to, I'm going to change this, is equal to CM delta T. All right, well, they really simplified this up for me in that they gave me the specific heat capacity straight up. That was easy. Okay, and the unit is Kelvin, but it can be Kelvin or it can be Celsius. It doesn't matter. I'm just going to write Celsius for clarity for one of the steps. All right. They also gave you, well, they didn't give you a simple thing here. What do they give you in terms of mass? Kilograms. So this 50 kilograms can't be used directly. That's not kilojoules. Kilograms. And so I do have to do this. Kilograms to grams. 1 kilogram is 1 e to the third grams. But they did give you this. They just told you the temperature change was 12. It's positive. The rocks heated up. Okay? And if I look at the question, calculate the quantity of heat absorbed by rocks. It's talking about the solution itself. So if I do that calculation, somebody actually put something in the calculator. What do you come up with? $492,000 joules. Okay, I can write that differently. I can do 4.92 e to the what? 4.92 e to the fifth. Good. Okay. It's a pretty big number because you heated up a lot of rocks. And since it is the solution, I use the calculated value. Okay. So that is cool. All right, let's go to the next. Oh, check this out. There was answers underlined. No. Stop, stop, stop. Go back. Huh. All right, lost all of that. Okay. Let's go to the next one. Okay, so what temperature change would these rocks undergo if it emitted 450 kilojoules of heat? Okay, I come back to here. Q equals Cm delta T. All right, in B, it told me an energy value, 450 kilojoules, right? But what happened to those kilojoules? They were what? Lost. When I lose, what is the sign of the value? Negative. It lost 450 kilojoules. Now, in my equation, can I use kilojoules? No. So I have to change kilojoules to joules. 1 kilojoule is 1 e to the third. Do I have a heat capacity? Absolutely. Got that. Do I know how many rocks that are there? Oh, yes, I do. Kilojoule, kilograms, 2 grams, 1 to the third. And what I want is a delta T. What do you come up with? On what side? Yes, it is 41,000 on this side, right? For that number is 41,000. What's the number on this side? Right? Take 450,000 and divide it by 41,000 so that you get delta T all by itself. What did you get? Because that's the value of that numerical. That's the value of that numerical. 41,000 on this side. So that's 41, and that's 450. What did you get, Justin? Negative 10.98, and if you get it to 3 sig figs, it would be 11, correct? Now let's think about this. The rocks give off heat. What would happen to the temperature of the rocks if it gave off heat? The rock temperature should go down, and it should go down by, in this case, 11 degrees. Okay? And so the negative signs make sense. All right. This calorimetry is called a constant pressure calorimetry. It's basically the styrofoam cups. This is the kind of instrument that you use. Now, we do have a bomb calorimeter. Okay? It's also called a constant volume calorimeter. It's a reaction that's carried under constant volume because it's encased. It's this container that is metal, okay, filled with water, and in this case, it's a very, very thick metal container that gets screwed on. And so what you do is you put in your material, you pump in oxygen, okay, and you heat it until it explodes completely, okay, or combusts completely. So, how often do you think I would let a freshman take a metal container, add oxygen, put it all together, and heat it up, make it explode? I don't even like giving it to seniors without another faculty member there to watch them. Okay? There's a little bit of danger with these, but if you do it under controlled conditions, you are able to do this. And this is a way in which we can calculate how much energy value happens. Now, where in real life would we use this? You know all those calorie items on your food? This is the kind of experiment that we do to calculate how much energy is in the food. Okay? And so there is something that we would technically get. Now, this calculation value is a little bit simpler. The reaction is equal to the change in temperature that happens times the heat capacity of the calorimeter times the negative sign. Now the heat capacity of a calorimeter for this one is in a value of kilojoules per Kelvin or kilojoules per degree Celsius. Okay? How in the world do you know when you use the other equation or you use this equation? All right. You read the question. If it says bomb, use this one. If there's no bomb associated, use the other one. Okay? That's it. And so here is an example of the type of question you might see. A 1.8 gram sample of octane C8H18 was burned in a bomb calorimeter whose heat capacity is 11.66 kilojoules per degree Celsius. The temperature of the calorimeter plus the contents increased from 21.36 to 28.78. What is the heat of combustion per gram of octane? Okay. Well, first of all, to find out how much the heat of combustion is, we use the equation at the top. And so I will do this equals a negative sign times the heat capacity kilojoules per, in this case, degrees Celsius times final 28.78 minus initial. Okay. And so, can anybody do that for me? 11.66 times the difference between 28.78 minus 21.56. Negative 84.185. Does anybody get that? That
84.1852.
1852. Yeah. Negative 84.1852. That. Okay. That's familiar to me. All right, that's the amount of energy came off, but it wanted it per gram, so I do this. That comes out to what? Where do we get that one? Negative 46.777. Close enough for government work. Okay. Now, if you get this value, the next question, per mole of octane. Oh my goodness. What in the world? If this number is correct, kilojoules per gram, then what I have to do is change grams of this into moles of this. Well, how in the world do I do that? I'm going to round it. You would get this wrong on Chem 21. I know carbon weighs 12 times 8 plus another 18. It's 114 for every one. I know that is not the true number. That's a good guesstimation. Negative 46.77. It would come up to, that doesn't look right. $5,332 kilojoules per mole. A lot of times, the calorimetry with the bomb isn't just telling you or asking you how much energy is given off. It will take that energy and relate it to how many grams there are or how many moles there are. I don't know why it does that step, but that happens quite often. Oh, we were off just a little bit, but I don't know why. We got there. Oh, there's the real values. I don't know, something happened in our calculation. All right, let's try this one. Why don't you go ahead and work on this in groups, and we'll show that in just a moment. So, find a partner. Or do it on your own, and then see who is right. Anybody get close to those numbers? Hmm?
I said we'll be there in just a sec.
Be there in just a sec. Oh. Let's see. 15 point. My rounding was different than theirs. Yeah. Their rounding was different than mine. I didn't take out the molecular weight to the CHEM-111 value. I said carbon weight 12 times 3. I said oxygen weight 16 times 3. And I added 6 for the hydrogens. So I know that that is slightly off. But it's good enough for a quick example.
We got 1,367.
67, yeah. And so it's really, really close. In terms of if you're doing this and the written part on the exam, that's fine. All right. Okay. All right. Calorimetry. We are done. This is one way in which to calculate the value of how much energy is being given off of a reaction. Okay. Now we're going to do other ones. All right. And what we're going to do is we're going to look at what's called bond dissociation enthalpy. Okay. Remember what enthalpy is. Enthalpy is H. We usually say delta H, which is Q at a constant P, which is heat at a constant pressure. Okay. Which is equal to E, delta E, because Q is W and we have no work. Okay, and if we do it at constant pressure, that's why we use enthalpy. So there's where that word comes in. All right, this is the energy needed to break a covalent bond. And so the bond has 2 electrons at least being shared, could have 4, could have 6, depending upon double, triple bonds. Okay, and to break that bond, it requires some energy. Every bond has a different value. And so if by chance I say D subscript Cl-Cl, it means I'm breaking a Cl to Cl bond. Okay, and it will require the investment of 242 kilojoules to break a mole of those. Okay, now to actually determine each individual bond is kind of hard. But if by chance I break, let's say, this molecule, and then I calculate a value of energy it takes to break it, well, there were 4 CH bonds, and so I can calculate the value of each CH bond. And so that is a measured value. It's an experimental value. Okay? And so what this does is produce for us a whole chart of values in very, very little tiny type. Okay? And so these are positive numbers because to break a bond, you have to invest energy. All right? And so you can see different values are given there. But what's important is, these are all single bonds. If you get to double bonds, the values get bigger because the double bonds hold stronger. If you get to triple bonds, those are even larger values. Okay? But you're going to have to use a table to calculate these values, to calculate the problems. Multiple bonds get bigger and bigger, and so these are average bond enthalpies, not the absolute, okay? Because the amount of energy in as a bond is actually influenced by what is there, and so if you've got a carbon that has 4 hydrogens around it, there's a value for each of the bonds to hydrogen. If there is a value of carbon with 3 hydrogens and 1 chlorine, the bond changes because the chlorine's a little bit more electronegative. It pulls the electrons a little bit, and so all the bonds are a little bit different because of that electronegativity. But we get good estimations by using the average energy that are in these tables. And so we get very good estimates of about what the reaction should be overall. Now, here's what we're going to do. We're going to take, we're getting into some real math stuff. What is that? Sigma. Oh, I guess it should have been written in blue, not red. Okay. Sigma means what in math?
Sum of everything.
The sum of everything. So I'm going to take the sum of all the energies for bonds that are broken. And then I'm going to subtract the sum of enthalpies for all the bonds that are formed. Okay. And if I can do that, then I will come up with the energy, the enthalpy of the reaction. All right. So I just take up and I take the number and the values of those that were broken minus the values of the ones that were formed. Okay? Oh, that's all well and good. But you got to decide which ones are broken and which ones are formed. Okay? And so to calculate these, you have to have a table. Okay, I have to give you some values. Then you have to identify which ones are broken, which ones are formed. And then you got to add up all the ones that are broken, add up and subtract all the ones that are formed. And so you're going to be given equations that look just like this. All right? But can you actually see what's broken and formed? Maybe, maybe not. Okay. Oops. All right. What do you have to do to this thing to actually see what's broken and what's formed? Okay. Do you even see a bond here? Do you see the bonds? Have I written bonds out? What was the structure that actually shows bonds? What is that structure called? A Lewis structure. So, Lewis structures. To do this problem right, you have to draw 4 Lewis structures correctly. Okay? So, if I draw... Ooh, stop. To get this done right, I have to do this. C, H, 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 Cl, okay, in my head, I added up all the valence electrons. I decided what was central. I added 1 atom to each on the outside. I then fulfilled the octet of all the outside. Then any extra electrons went onto the central atom. I calculated the formal charge to find out if it's the right thing. I did that all in my head. You might not be able to do all that in your head, but those are all the steps that are necessary to get that done. All right? Now, I did that just so I could begin this problem. All right? In this case, when I look from the front to the back, what is missing? What is new? Okay? Is this bond in the end? This carbon to that hydrogen in that position? Yes. Nothing happened. This one to the one down. Did anything happen? Nope. This one to that one. Anything happen? Nope. This one to that one. Is this one missing? Yes. This is a broken bond. In this, is there a chlorine to chlorine on the other side? No. I broke that bond. There are 2 bonds that are broken. Okay. What is new on this side? Out of this one, what's the new one? The what to what? Chlorine to carbon. And is there any new one in here? Yep. Hydrogen to chlorine. Okay. And so I've decided what I have broken and what I have made. I have broken a carbon to hydrogen and a chlorine to chlorine, and I've made a chlorine to carbon, a chlorine to carbon, and a hydrogen to carbon. Okay. And so, to do this, you take all the bonds that were broken minus all the bonds that were made. And to get these values here, 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 and here, I have to look up on a table. What is the value of a bond like this? Based upon what this slide says, what's the value of a Cl to a hydrogen? (431). It doesn't matter which direction, and all those numbers are in kilojoules per mole. Don't let it confuse you if you got it backwards. If you've got one thing bound to one thing, it doesn't matter which order. Okay? All right. Bonds broken minus bonds formed. That is simple, right? That idea is simple. What's the harder part is identifying. Now, sometimes you might not be able to identify these real well. Here's a way you can always get it right. It's longer, but you'll always get it right. Break every bond, make every bond. If you can't identify which ones were broken and which ones were made individually, break them all, make them all. Because if you did that, you would have broken 3 CHs here, and you had 3 CHs there. They would net out. Okay? But if you can identify them, it makes it shorter. If not, you can break everything. Watch this thing. All right. C to C. What is made, what is broken? In the reaction I just wrote out up at the top. This one, that is different. What did you break? What did you make? Discuss. Okay. Anybody want to jump out on a limb? What did you break? You broke. Oh, man. Please don't make. Okay. Whoop. You broke. Come on. I lost all my work. No. Okay, there it is. You broke this. Is there anything else that you broke? A hydrogen, 2 hydrogens. What did you make?
2 carbon to hydrogens.
2 carbon to hydrogens. You did not break just 1 carbon to carbon bond. You actually broke a double bond. You also made one more thing. You also made a carbon to carbon single bond.
So it has to break completely. It's
You
not
have to
accepted.
combine, yeah, you can't just break part of it. You have to break a double bond completely, and you actually made a single bond, carbon to carbon, because there was not a single bond in that front, in the reactant. You also made 2 carbons to hydrogen. So that's a little bit tricky when you use double and triple bonds. You must break them completely and then make what is new. Okay? That could be tricky.